Jeff Vetsch manages soil science research at the University of Minnesota Southern Research and Outreach Center in Waseca. Jeff is a certified professional soil scientist. He received his Master of Science degree in soil science from the University of Minnesota. Please welcome Jeff Vetsch.
So why are we talking about nitrogen in southeast Minnesota? Well, there's several reasons. Obviously, nitrogen management is important, but well testing has found elevated nitrate in groundwater in southeastern Minnesota. And when we look at this map over here from the Department of Ag well testing program, you see these townships in red. Those are ones that are more than 10% of them are testing above the drinking water standard of 10 milligrams per liter. The ones in pink are 5 to 10%. And it's not just a southeast Minnesota issue. Up here along the I-94 corridor and these irrigated sandy soils, we have some of the same concerns. When we think about what the driving factor is of this nitrogen loss that's getting to groundwater, is nitrate moves well with water, especially through these permeable soils. Permeable soils we would find in these central sands as well as the ones we find in southeast Minnesota. What's unique to southeast Minnesota is underlying those permeable soils and sometimes very shallowly, meaning that there's not a lot of topsoil over this fractured limestone bedrock. And then once it gets to that bedrock, it finds cracks and fractures and ends up in groundwater fairly rapidly. The land use in these areas, in many of these areas in red, is primarily ag, corn, beans, row crops, livestock, some small grains, some forages, but primarily corn, beans. The history of nitrates in groundwater in Minnesota, interestingly enough, Warren Formo is sitting out front. He just wrote an article for The Farmer. So if you want to, on the history of this, if you want to find that, it's in the February issue. But in the 1940s and 50s, there were over 150 cases of what's known as blue baby disease. And that is, can be fatal. And there were some fatalities back in that period. But there was some education that was done, there was some testing, and for the most part, that problem was primarily solved, and there was only 2 cases in the late 70s, early 80s, and there's been no reported cases of that since then. However, there's still concern with this amount of wells that are testing above this drinking water standard. The Minnesota Center for Environmental Advocacy back in April petitioned the EPA, and they want to see something done about this. And it's more of not what we're doing, it's concern that there's not enough being done and some of the things that we are doing maybe aren't working. So it's kind of a 2-part concern. I think part of what has drawn more interest to this again now is not necessarily the blue baby disease, but a couple of journal articles, some out of Europe, some out of Iowa and the Midwest, has shown a potential cancer link between high nitrate consumption for adults and adults that live in areas with ag. So that is part of the issue. If you're interested in that, you can find that at the NIH website. And if you want to look at the township well testing program, you can find that on the Department of Ag website. So we know a lot about nitrogen management in Minnesota. We know where our sensitive soils are. The coarse textured soils are well drained. They're going to have leaching potential, and the karst topography. So our nitrogen management is broke down by not only the soils, but the climate. It's wetter to the east and southeast, and it's drier to the west. So there's the potential for nitrogen loss is less to the west where it's drier, especially in the northwest. And it's also affected by the crops that we grow. We also know a lot about the nitrogen uptake patterns of our crops, in this case, corn, which is the one that gets the majority of our nitrogen in southern Minnesota. We know from this data and other data that's similar to it that the uptake pattern for corn is highly dependent on this period between V6 and about R2. So if we have soils that have a high leaching or a high nitrogen loss potential, targeting our nitrogen applications during this period here near this rapid uptake phase is ideal to help minimize those potential losses. I think another thing that's shown in this curve or in this chart that's not talked about very much, but it's really important, is this translocation of nitrogen from the plant to the grain. Here at R2, we've taken up almost 80% of the total N that plant's going to take up during the growing season. We take up another 20% getting to R6, but you see this blue portion is the amount of N that's taken in the grain or removed from the field. And you see that over 50%, almost 60% of the N that's taken up by the plant is removed from the field in the grain. But after R2, the uptake pattern slows dramatically. So where does the rest of that N come from? It comes from other plant parts that are mobilized or translocated to the grain. And why that is important is when you're looking at walking your fields at R4 or R5, and you see lower leaves or stalks that maybe are starting to turn yellow, I think some people get concerned and panic that, oh my gosh, I've got nitrogen deficiency. Part of that is just the natural translocation of that nitrogen from the plant where it's not needed, plant parts, especially lower leaves, to the grain where it is needed. And you shouldn't be that concerned about it, and you don't need plants that are green from top to bottom, especially as you get back to these later growth stages, R4, R5, and R55. One of the challenges is increased precipitation has caused more nitrogen potential losses, both due to leaching and denitrification. Where are we seeing greater increased precipitation? In southern Minnesota, primarily the southern 1/4 of the state. These areas in dark blue, this is spring precipitation change from 1950 to 2021. And you see about a 25% to 27% increase in this region. That coincides with our annual precip increases. And at Waseca, where we have over 100 years of climatic data, we do our traditional 30-year normal periods where we look at the average or normal precipitation in a 30-year period. And back in the 1941 to 70 period, our normal for Waseca was right around 30 inches. In our last period, which was just a couple years ago, 1991 to 2000, we are now just barely under 38 inches. So that's a 26% increase during that time period. And that added precip is definitely affecting our nitrogen management. When is that precipitation occurring? Here at the top, we have the monthly breakdown in inches and the total. This is 51 to 1980, and down here is 1991 to 2020. All months have increased in this last 40-year period. June is currently our wettest month, but May through September at Waseca are all over 4 inches. The growing season is getting significantly wetter, which is good from a crop, evapotranspiration or uptake potential, but also is troublesome in these early months when precipitation often exceeds evapotranspiration and you get more leaching and potential denitrification losses. Now, we would recognize that in the recent years, the last 3 or 4 years, we've seen more drier conditions, but these trends of increased precipitation are more long-term. So it was about 10 years ago that I was talking to a colleague of mine, Kevin Keener with the Department of Ag in Southeast Minnesota, and he asked me, he said, would you be interested in doing some research on farmers' fields and working with their stakeholders, not only the farmer, but their crop consultants, their fertilizer retailer, because we know they're very influential in the decision-making of nitrogen management on the farm. So he asked me if I was interested in doing some on-farm research and working with these individuals, kind of in small groups, to see what impact we could have on making some changes in maybe their nitrogen management, or just helping them better understand where our guidelines and where our recommendations come from. So the goal of this study was to increase confidence in and adoption of our current best management practices in Southeast Minnesota. So the study involved small rate and rate trials on a farmer's field. We try to stay there for 3, 4, maybe 5 years, because I wouldn't recommend anyone do something once on their farm and then go make a bunch of changes. You need to build some confidence and you need to have repeatable results before you'd feel like you want to make a change. So we look at the effects of nitrogen rate and application timing on corn yield, nitrogen use efficiency, net return, and residual soil nitrate. The methods over this last 9 years, we have 24 site years from 2015 to 2021. And during that period, we had 7 N rates that were applied either pre-plant or at planting and 3 split application treatments. And in 2022 and 2023, we changed the study a little bit, added to 12 treatments. We have 5 pre-plant application treatments, 5 side dress, a control, and then we have a blend of ESN and urea. And the purpose of that is an alternative to doing split application. Maybe I can put this ESN urea blend out there and I don't have to split apply. And this study is funded by the Clean Water Fund through the Department of Ag. And the pictures over here show some N deficient plots and how they're laid out in the field. So the primary data that comes from this study is over here on the y-axis on the left is grain yield in bushels per acre. This is the total nitrogen rate applied on the x-axis. These black circles are the mean values of the 4 reps of the pre-plant N rates. The triangles, the blue and the red, are the split applied treatments where either 1/3 or 2/3 of the N was applied at planting and the rest was applied at side dress. This is a corn after bean site. And on this right y-axis is the residual soil nitrate nitrogen in the 0 to 4 foot depth after harvest. And that's our measure or our kind of guideline to look at how we're doing from a water quality standpoint. How much nitrogen are we leaving in the soil after harvest? So this site was in Grand Meadow in 2019, and this was a site that the split application treatments did quite well. They produced a similar yield, but at a lower N rate. And this diamond is the calculated MRTN, or maximum return to nitrogen, or I might use the term economic optimum N rate. They're basically synonymous. So this busy chart is 13 site years of corn following soybeans in southeast Minnesota. And each of these curves or lines is the response curve function calculated through the software. And then the corresponding colored dot is the economic optimum or maximum return to nitrogen for that individual site. This shaded box is what we consider our acceptable N rate range for corn following soybeans, which is 130 to 150 pounds with a 0.10 price ratio in the corn N rate calculator. But that is the 2023 data, recognizing that some of these sites were done significantly earlier when that box would have been shifted to the left and have been a little lower. What we see in this database is 3 of these sites were below the minimum, or the economic optimum for 3 sites was below the minimum of the acceptable range. 4 fell within the range. 3 are right here at the edge of the maximum of the range, which I think is generally a pretty good area to apply, right around 150 pounds. And then there were 3 sites that were out here quite a bit farther or needed considerably more N than we would recommend. One of those sites included a 30-pound N credit for DAP that was applied in October the previous year. And this is troublesome, but it's also part of our recommendation guidelines. We should include all nitrogen sources, but if we're applying a couple 100 pounds of DAP in the fall, early in the fall, whether or not that nitrogen from that DAP is going to be available by the next summer when this corn crop is grown, it depends. And Bobby and I did a study back in the mid-90s, and about 1 out of 3 years, we did not see much of that N available. So I think that contributed to that one site that needed significantly more N. When we look at some of the trends in this data, it's interesting that 4 of the 5 sites that needed significantly more N than our recommendation, and some of these are just a little bit more, they were all at Grand Meadow. And Grand Meadow, even though it's in the eastern edge of Mower County, it's still considered in the karst topography. It's right at the edge of it. But the Grand Meadow soils are unique in that area, is that it's actually a poorly drained soil, and it has tile, where most of the loess soils in the karst are not poorly drained. They're well drained. Most of them are untiled. This Grand Meadow site has what I would consider an old dense till, and it's at about 1.5 to 2.5 foot depth at this one farm. And it creates kind of an impermeable layer, so water movement is not very good through there, and even root penetration of that dense soil is difficult. And what we see in that site, even though this site has soil organic matter that usually ranges from 4.5 to 5.5%, one of our sites was 8.8% organic matter, it does not produce much mineralizable N. This is corn after beans, and we're getting only 100 bushels, and in some cases less than that, with no nitrogen, which is pretty unusual in a corn-soybean situation. So what stands out at this site is that this poorly drained soil near Grand Meadow actually does not mineralize as much N as lower organic matter soils to the east of it in the traditional silt loam loess areas. This crazy graph or chart is looking at monthly precipitation as a percent of the 30-year normal for these corn following soybean sites. I've color-coded the boxes, so if they're yellow, that means that the rainfall in that month at that site was between 125 and 150% of normal, so between 25 and 50% greater than normal. If it's a red box, it's greater than 150% of normal. And in some cases, the numbers here like 232%. So over 130% more than normal rainfall at that month in that site. And we know that excessive rainfall drives N loss and both from leaching and denitrification. Down here at the bottom, I've got the MRTNs at these sites. And when we find a site like here where we needed 203 pounds, which is significantly more than our current recommendations, it's interesting to look at were there year or months in that, especially spring months, that drove a lot of N loss. And at this Grand Meadow site, there really was not. But it did follow a previous fall that was wet. Here's a site that needed 198 pounds, and that's the site at Grand Meadow in 2019. And that was an extraordinarily wet growing season, which both had a wet spring, a wet fall, and followed a extraordinarily wet fall the previous year. And then over here at Elgin, you see a couple of these sites. This one only needed 151 pounds, but it also was a fairly wet growing season, but more of the moisture or excessive moisture came in the fall. So at these corn soybean sites, some of the higher end demand could be explained by excessive rainfall, but not all of it. These are the N rate responses we found for corn after corn in southeast Minnesota, and there's 11 sites here, and one site needed only 100 pounds. We would recommend 160 to 190 at the 0.1 price ratio. 4 of the sites were below that range minimum. 3 sites fell within the box, and 4 sites were above it. What was interesting is the mean of the MRTN for this data is 178, right within our recommendation guidelines. The median is 166, but the range is 100 to 270, and 270 was our maximum N rate at that location. So in these corn on corn sites, we saw a much greater range in optimum N rates, and trying to predict that or explain that was more challenging. And we did occasionally see sites that had low N availability, but it's this continuous corn that would be expected. We also had sites that produced 150 and one that produced 180 pounds of N with no nitrogen, which is pretty unusual. And only 1 or 2 of these sites had a significant carryover of nitrogen that we measured in the pre-plant N test or pre-side dress N test during the growing season. But one of the things when we look at the monthly precipitation chart for these corn on corn sites, we see that several of these sites that needed a lot of N, 240, 270. The 2018 Harmony site was the wettest year in the state or in the state of Minnesota. It had over 60 inches of rainfall, broke the state record. Then the next year had a wet fall, but it followed this extraordinarily wet year, and it needed 270 pounds. And the same we found over here at Utica. We had a year that was wet in the spring, but 165 was adequate. We had another wet year and another wet year, and the N demand was increasing. So it seemed like the precipitation was a better pick or determinant of, or excessive precipitation was fairly accurate at predicting where we needed more N in corn on corn, but less accurate in corn flung soybeans. How effective was split application? Of these 24 site years, 5 of them responded with a significant yield increase to split application. So that's only 21% of the time. And ironically, only 1 or 2 of these sites had excessive spring precipitation where we would expect pre-plant or split up, or we would expect split application to be superior to pre-plant. This is the residual soil nitrate at a 0 to 4 foot depth. And this is our nitrogen rate, total nitrogen rate minus the MRTN or the economic optimum at a given site. So this is our vertical 0 line. So if we're over here to the left of that, we're applying less than's needed. If we're applying more than's needed, we're on the right of this. And what you see is that when we are somewhere near MRTN, we are not leaving a tremendous amount of nitrogen out there in the profile to be lost to groundwater or surface waters in the Grand Meadow area. And actually being significantly less than optimum really is basically just staying right at this background level of 30 to 45 pounds of nitrate left in the profile. But once we get to about 50 pounds in excess and certainly above that, not only do we see a lot of variability, but we also see the potential for a lot of nitrogen left in the profile, which could be lost. the next year or that subsequent fall. So to kind of summarize this first 6 or 7 year period, applying near the max of the MRTN acceptable range, which was 150 pounds for the current one, optimized either yield or economic return, 10 of 13 corn after soybean sites. 3 were under applied and 3 were over. But for corn after corn, the EONRs range from 100 to 270. So we obviously need to develop other tools and use other tools to help get a better handle on the end need for these corn on corn sites. Excessive precipitation explained some of these things, especially in the corn on corn sites, but it did not explain them all, or some of the demand for higher N. Other factors like soil N supply, mineralization potential, that was clearly a factor at that site in Grand Meadow, where we just don't seem to get the amount of N from that soil organic matter that we do on the lush soils that are well drained. Split applications of N increased yield at 21% of the sites. From a nitrate contamination, applying N rates greater than economic optimum or MRTN increased our residual soil nitrate, which is the risk for contamination of groundwater. And the literature is pretty clear: whenever you increase N rates, you increase the risk and the potential for nitrogen loss. We did an impact survey with the stakeholders, the farmers, their ag advisors, and their crop consultants. After the 2022 year, 46% of them that participated planned to reduce their N rates after seeing this data on their farm. 92% were somewhat or extremely likely to discuss the results with other farmers and or their advisors. And 90% made some kind of N management changes based on these results. So I'm going to go into what kind of the changes that we've done the last couple of years and some of the data that we've seen for the last 2 years. So this is the effect of N rate over N rate on yield, the response functions for both pre-plant and split applications at the same site. So the black circles are the pre-plant or at planting N rates. The triangles that are in gray are the split applied treatments. At this Grand Meadow site, this was corn after soybeans. The EONR for pre-plant was 150. For split, it was 160. But the split applied treatments produced about 6 more bushels, and that was statistically greater. So just a slightly greater N need than our maximum of our acceptable range, but split application was superior at that location. We have this ESN urea blend treatment, and at 117 pounds, that blend averaged 218 bushels per acre, but that was actually 10 bushels less than the pre-plant application. We also have PPNT, pre-plant N tests, and pre-sidrus N tests, and we look at whether or not those are good predictors of whether or not we have adequate nitrogen during the growing season. This is the residual soil nitrate data from Grand Meadow in 2022. And we see that when we were below the economic optimum, we had very little residual nitrate left in the field. Once we got to 50 pounds above, we increased it slightly. And once we got to 100 pounds greater than needed, we started to see it increase. This is the Elgin site in 2022. It's also corn following soybeans. And at this site, we needed 70 pounds less nitrogen when we split applied, which is a really large difference. And I would not expect that very often or ever to see that in a site. But that's what we experienced. This site had a very high, or relatively high, medium high grain yield with no nitrogen of around 150 bushels. And you compare that to this Grand Meadow site, again, that's only producing about 100 bushels. The ESN blend was similar to the pre-plant and a little bit less than the split applied. And the PSNT did a fairly respectable job of predicting that we would need less N with the split application compared to the pre-plant. The Elgin site, since we needed less N, we had a little bit greater N in the leftover in our residual soil nitrate, but it really noticed that there was more RSN left where we split applied, but we also used less, or we needed less with the split application. So the point of this is that if we're going to do a split application and we seem to be getting better efficiency from that, we need to be thinking about the rate that we're applying so that we're not leaving extra N out there by just going to a split and then having a higher N rate and leaving more N in the field, which could be lost. This was a Harmony site. This was corn on corn. And again, we needed about 30 pounds less N where we used a split application versus pre-plant. And the PSNT here was 6.6, or the PPNT was 6.6 part per million. So there was a little bit of carryover N from the previous year at this site, but it's just barely over that critical value of 6. So we could credit it up to 35 pounds, but it's not a large number over 6. It's a 6 to 9 is the range. So the credit would be marginal, I think, in that case. The Harmony site, again, we did not see significant amounts of nitrate left in the profile until we got, 50 to 100 pounds greater than what N was needed for the site. This Dover site in 22 was unique because it was corn following sweet corn, and it also had a cover crop that was oats and radish. And it did not need very much nitrogen in 2022. The pre-plant economic optimum was 135. The split was 112, or about 20 pounds less. But this is 25 to 38 pounds less than our minimum of our recommended range for the corn following soybean, or for corn on corn, which is 160 to 190. And this was a site where the ESN urea blend actually did well. The Dover site, since it did not need much nitrogen, did have a significant amount of carryover N after the season in the RSN. Especially when we got to 180 pounds and greater, we saw significant amounts and up to over 200 pounds of N with these 300-pound N rates. So in 2023, we saw very dry conditions at all these sites. In 2 of them, we had less than 50% of normal growing season rainfall. So we would not expect to see much of a response to split application like we did in 2022. And that's exactly what we found. At all 4 sites, there was really no difference between the pre-plants and splits. At this Grand Meadow site, we needed about 169 to 174. We still had very good yields, 236 to 237, which was very surprising. This site had 15 pounds of N in MAP and starter. We credited that in the total N rate. It also had a biological that was applied. I did not credit that at this, or in the total of nitrogen. The PSNT, it was greater than 25 part per million, which is the critical value for Iowa State at 115 pounds. That's back here. We clearly needed more than that. I think in 2023, using the PNT or the PSNT in particular in these sites that get some pre-plant N is very questionable because it's so dry that all that N stays in the top 6-8 inches or a foot of soil, and we're getting very high PSNT values in early June, and I think it's not going to be a very effective test in these very dry springs if the site had pre-plant applications of nitrogen. The Grand Meadow site generally had a little bit higher nitrate, but it didn't really become considerably greater until we got up to about 215 pounds of nitrogen or greater. At Elgin, again, we saw no response to pre-plant versus split. We needed about 125 to 137 pounds. We still produced a very respectable yield of 234, and this was a site that only had 46% of the normal growing season rainfall. Elgin did have a fair amount of residual soil nitrate, especially after we got up to about 162 pounds and above, and that makes sense because it was a site that did not need a lot of nitrogen to reach optimum yield. Harmony site needed very little N. This was corn on corn, only 80 to 86 pounds. It produced 205 to 208. That's 74 to 80 pounds less than our recommendation, or the minimum of the acceptable range, which is 160. There was a lot of yield variability, some in the checks and at this first N rate. And I think that was just due to moisture and just subtle elevation changes in this fairly small area of this field. The PPNT here was under 6 part per million, so no credit would have been applied based on the PPNT soil test, but still we needed very little nitrogen. Interestingly though, the PSNT was greater than 25 part per million at 120. So the PSNT was better at predicting that this site would not need very much nitrogen. Oddly enough, even though the N demand at this site was really low, we did not leave much N left in the profile. which is really a bit puzzling at this location compared to the other 3 locations in 2023. The Dover site last year in 2022, again, it was corn, falling sweet corn with a cover crop. In 2022, it did not need very much N, but in 2023, it did. It took 200 to 210 pounds, which is only 10 or 20 pounds more than the acceptable N rate range for continuous corn of 160 to 190. It had a very high yield at 0N, 176. So this response curve function is very flat. It did not use its nitrogen very efficiently. And I think what's going on, and it did have a PPNT of 8 part per million, so it would have been allowed to have an 8 or 35 pound N credit, and the PSNT was greater than 36 at only 60 pounds of N. So the PSNT would have not worked very well to determine how much N the site needed. But when we took the residual soil nitrate data, what we really found is we found a lot of nitrogen left in the profile, even though it had a higher end demand. I say, well, how's that possible? Almost all of that, 80% of that nitrogen was in the top 2 feet of soil. It was not available or really available to those plants. The plants were taking up water a lot deeper than that because it was a very dry environment. The still was a very good yielding site. It yielded 241 or 242. All that nitrogen it was looking for, it was scrounging or taking from deeper in the profile, and all this N laid in the top foot, and it couldn't use it. And it was still there. We look at the precipitation map. All the sites in 2022 had at least 1 month in the spring or summer, or at least 1 or 2 rainfall events where excessive rain occurred and leaching or denitrification could be possible. But for the most part, these were relatively dry or normal years. Unlike that in 2023, all these months during the growing season were incredibly dry. Here, only 7% of normal rainfall at Elgin in June. And we look at the growing season totals, May through September, 58% of total for Grand Meadow, 66% at Elgin, 46% at Harmony, and only 44% at Dover. So this is kind of part of what's driving the N demand. In some sites, it didn't take very much N, and others it did, and it's just very unusual weather patterns. So applying N rates within the MRTN acceptable range, optimized yield or economic return at 5 of the 8 sites when N was split applied during this 2022 to 2023 period. 2 sites needed less, 1 needed more. But when N was applied either at planting or pre-plant, 5 of the 8 sites needed more N, and it averaged about 25 pounds. Why did split application do so well in 2022? Like I mentioned earlier, every site had either 1 month or 1 or 2 excessive rainfall events that were 1.5 inches, 2 inches, and a couple of them had events that were greater than 2 inches or had a moist profile and another significant event, even though the growing season rainfall was near normal. But in 2023, nearly all these growing season months had less than normal precip, and there really were no rainfall events greater than 1 inch at most of them. Split applied N only increased yields based on the ANOVA statistics at only 1 of the 4 sites in 2022, but all of them had numerically greater yields, and there were no differences though in 2023. The risk for nitrate contamination of the water due to leftover nitrogen, split applied N rates at rates greater than the MRTN, and that in 2022, the MRTN for the split applied treatments was often less than it was for pre-plant. But where we had excessive N, we generally left a fair amount of N in the profile, so it would be potentially lost, could be potentially lost. In 2023, the residual soil nitrate was generally greater than what we saw in 2022. It was an extraordinarily dry year, so I don't think that's too surprising. At Dover and Elgin, the majority of that RSN was in that 0 to 2 foot increment. It's just basically it was positionally unavailable to that crop to use it for the plants, due to fairly extreme drought, especially in June and July and into early August. These sites would be good potential sites if they were going to return to corn the next year to do a PPNT this spring and see if some of that N is still there and credited. With that, I'll stop, and I'd like to recognize the funding for this research was provided by the Department of Ag through the Clean Water Fund and also from the U of M Ag Experiment Station. And thanks to Don Bernal, Kevin Keener, Sarah West, Michael Cruz, Kyle Holling for all their contributions to this work, and to the farmers and collaborators for this study. And you can follow me here on Twitter or X. Time for questions? So could the higher residual soil N in some split treatments have to do with sampling time relative to the last N application timing? So I think yes, in some regards it does. The side dress treatments were generally applied at V5 to V6, so it's usually the first week or 10 days of June when the split application. In these latter 2 years, we were applying the majority of the N at planting and only a smaller portion, generally either 40 or 50 or 60 pounds of N at side dress. So the majority of the N was going up front. But yeah, I think the timing of soil sampling does play a role. Generally, we would soil sample these sites after harvest in mid to late October, but 1 or 2 of these sites didn't get sampled till early November. But in these very dry years, I don't think the sampling time is that critical to affect how much RSN is left in the field. Do you know if N fixing corn will be a reality in the next 10 to 15 years? No, I do not know. And I doubt that. There's a lot of work on biologicals and what impact they might have. And I think there's a couple speakers here later today that are going to talk about that. What percentage of the N was applied? Oh, that one went away. It appears your increased rainfall trend correlates to the corn yield trends. That's a good question. I think corn yield trends are primarily driven historically by genetics and also increases in population. I think planting population and density of seed has driven a lot of the yield increases. Precipitation trends may help for some of the marginal lands in the more arid regions of the Corn Belt. But when you looked at the state of Minnesota map, really the only regions that are seeing a significant increase in precipitation are that southern quarter or third of the state. The central part of the state and the north and northwest really had not seen much of a trend towards increased precipitation. Time? Okay, thank you.